Alright, so last we left off, we were talking about running an apartment complex and some rules, and it looked something like this. Now, I'm not going to go very slowly like we did in lecture. I'm actually going to speed it up a bit, but there is an extra rule, or a couple of rules that I want to add, so just kind of pay attention for this analogy. So it makes a little bit more understandable when we actually switch over to the actual electrons. So remember that we said for the first rule, it says we fill the available apartment buildings closest to the office first. That's the number one. Number two, no more than 2 people per apartment. That's pretty straightforward. And number 3 was, as we fill each apartment in an apartment building, we fill it with 1 person until all the apartments in that apartment building are half filled. Then we add the second person to each apartment. But now I've added one more rule, which I didn't say in the lecture today, or technically yesterday, or more technically, X many days since April 6, 2020. This is the new rule that I've added. The first person in the apartment gets the top bunk, the second person in the apartment gets the bottom bunk. So we're going to assume that each apartment has a bunk bed and they have to share, but that's the rule. The first person in, up, second person, bottom. And to make it pretty simple for ourselves, instead of drawing actual little people, we'll just go ahead and draw an up arrow for top bunk and a bottom arrow for bottom bunk. And yes, I know those are half arrows. Trust me, in the long run, you're going to be drawing a lot of arrows. It'll save time. And of course, we have those exceptions when we have 24 people or 29 people. Alright, so what I'm going to do to not waste time having to redraw the houses, I'm going to draw little lines to represent who's in each apartment. So as you can see, this one refers to the 1S, the 2S, these 3 are 2P, 3S, 3P, 4S, 3D, 4P. Alright, so let's say that we were going to put 7 people in our complex. As we go through the rules, this is the way it would work. The first person goes in the 1S apartment, top bunk, and we're satisfying all the rules. Then we move on to the second person. We don't put them in the second apartment building because we have to fill the available apartment buildings close to the office first, and we have this extra space, but it's bottom bunk. No 2 people in the same bunk. Person number 3 goes in 2S, top bunk. Person number 4 goes in bottom bunk of 2S. Person number 5 gets their own apartment, top bunk. Person number 6 gets their own apartment, top bunk. Person number 7 gets their own apartment, top bunk. So we're satisfying all the rules. Okay, what if we had 17 people? Well, we would keep going. Number 8 doesn't go in a brand new apartment building, or 3S. We go back and we start filling the apartments. So person number 8, 2P. Person number 9, 2P. Person number 10, 2P. 11, 3S. 12, 3S. 13, 3P. 14, 3P. 15, 3P. Then we go back and fill up the bottom bunks. 16, 3P. 17, 3P. And let's say I wanted to have a little notation or configuration that told me how many people were in the complex and in what buildings they were, and what apartments, and what bunk. Actually, no, it wouldn't tell me what bunk. It would just say how many people we have and what apartment buildings they're in. But because we know the rules, then we know what bunk they're in as well, and what apartment. The code would work like this. 1S, 2 because there's 2 people in that building. 2S, 2 because there's 2 people in that building. 2P, 6 because there's 6 people in the 2P building. 3S, 2. 3P, and there's 1, 2, 3, 4, 5. This is our configuration. And if we add up all those top numbers, we get a total of 17 because we have 17 people distributed in this apartment complex in these buildings. Now, in case you forgot or missed that exception, let's go ahead and pick number 24. What if we had 24 people? Well, then we would keep going. We left off at 17, right? So 18, 19, 20, 21, 22, 23. And if we just followed the typical rules, we would think that that's the correct notation or configuration. But it just so happens that naturally this person would much rather just have their own apartment since we're occupying the 3D building anyway. So this actually moves. It's not there anymore. It can be found here. Sorry, wrong color. It can be found here. So the configuration ends up coming out to 1S2, 2S2, 2P6, 3S2, 3P6, 4S1, 3D5. This is a much more stable configuration than if we had 2 in the 4S and 4 in the 3D. And really, you just have to know those two exceptions. So just remember that for 24, it ends in 4S1, 3D5. For 29 people, it ends in 4S1, 3D10 for the very similar change, where you take one from the local S orbital and satisfy filling half of all the apartments in 3D or all of the apartments in 3D. Same thing happens with 5S and 4D and some of the other ones down the line. So that's the basic analogy. And the premise is that as we keep adding more people, the size of your apartment complex is going to get bigger, larger and larger. Now, the buildings will not go on forever. Let's take an aerial view of your entire apartment complex, and we'll see the order in which the buildings need to be filled. Alright, so this is an aerial view of your apartment complex, and the general idea is that as we go this way, we are getting farther from the office, which means it requires more energy to cover more ground. Now you might notice that the buildings that are closest to the office are a lot easier to distinguish in what order the buildings that are closest to the office. Clearly 1S is before 2S, before 2P, 3S, 3P. But once you get out here, it becomes a little bit harder to differentiate what order they are closest to the office, which is why it's going to turn out that there's a lot more exceptions than just that 24 and 29 people scenario. But you don't have to worry about those. But I'm quickly just going to go ahead and tell you in what order these buildings will typically get filled. So it's going to be the 1S first, and then the 2S, and then the 2P, and then the 3S, and then 3P, 4S, 3D, 4P, 5S, 4D, 5P, 6S, 4F, 5D, 6P, 7S, 5F, 6D, 7P. So you might notice there's actually a method to this little madness. Alright, analogy over. The office is a nucleus. Each apartment in an apartment building is an orbital. Apartment buildings of the same color represent energy levels, or regions in space where we're likely to find an electron moving. Every apartment building is a set of the same orbitals, called a sublevel, and the electrons that are found in energy levels, the people that are found in the apartment buildings are really electrons. Also, energy increases as we go farther away from the nucleus, so energy levels increase as well. And the bunk bed, one bunk on top, or one person on top and one person on bottom analogy represents what's called the electron spin. Goodness. Okay, so let's go ahead and break down all these things. We'll start with electron spin. Alright, so electrons have what's called an electron spin, and this is a quantum mechanical property of electrons, and you can get super deep into, theoretical physics of subatomic particles and whether they actually spin and all that crap, but we're just going to keep it very simple for us. Because electrons are subatomic particles with a charge, as they move, accelerate, they generate magnetic fields. You can think of it like a magnet, where one end is north and one end is south. And for our sake in electron configuration, we're just going to label them. Spin up for just an arbitrary direction, and the other direction has to be the complete opposite, which we'll call spin down. There is your bunk bed, one up, one down. But you can kind of think of it like this. If we had two electrons in the same space and they both had north on top, you would expect some kind of repulsion between them. Just like if you took two magnets that had the same poles next to each other, they would repel each other. However, if you had one where north was on top and one where south was on top, then there's less repulsion going on there, and they can actually tolerate each other being in the same space. But we'll bring that up a little bit more when we get into our atomic principles. Speaking of principle. No, not Mrs. Valadez. We're talking about principal energy levels that are represented by the letter N. Principal energy levels are your major energy levels in an atom. So we're talking about the major regions of space where we are expected to find electrons. Principal energy levels are assigned values in order of increasing energy. So the first energy level is N equals 1, the second one N equals 2, N equals 3, and so forth. The average distance of the electron from the nucleus increases with increasing principal energy levels. So for example, the electrons in the third energy level are farther from the nucleus than electrons in the first energy level, on average. And within each energy level, there are what are called sublevels, or different orbital types, where electrons have probability of being found. The first energy level has an orbital called the 1s orbital. The second energy level has 2s, but it also has 2p orbitals. The third energy level has 3s orbital, or 3p orbitals, but it also has more space for electrons in 3d orbitals. You might notice that as we increase the energy level, we also increase the amount of electrons that can be housed within that energy level, and that's true. But also the whatever number of the principal energy level is also the total number of different types of orbitals that can exist in that energy level. Alright, so let's take a look at this table and try to make some sense of it. We're looking at the first four principal energy levels, which are represented over here, 1, 2, 3, and 4. We're going to be looking at the principal energy level, the type of sublevel, the number of orbitals per type of sublevel. We're looking at the number of orbitals per energy level, and the maximum number of electrons that can be found in that energy level. And what's kind of nice is that we have two little expressions or calculations that we can do to solve that much faster. So let's start with the first energy level. Alright, sorry, notice the typo there. Alright, so in the first energy level there is one sub-level type, and it is the 1s orbital, and there's only one, and that means that there's only one orbital in the first energy level, and that orbital is 1s. And if you recall, just like in the apartment analogy, no more than two people could fit in an apartment, no more than two electrons can be in an orbital, so the maximum number of electrons that the second energy level can house that the first energy level can house is 2 electrons. Now let's take a look at the second energy level. The second energy level has a 2s sublevel and a 2p sublevel. Now, the 2s sublevel, there's only one of those orbitals. The 2p sublevel, there are 3 orbitals, so that gives us a total of 4 orbitals in the second energy level. And again, because there are 2 electrons per orbital maximum, the most number of electrons that the second energy level can hold is 8 electrons. Moving on to the third energy level, there is the 3s sublevel, the 3p sublevel, and the 3d sublevel. There is only one 3s orbital in the third energy level. There are 3 3p orbitals in the third energy level, and there are 5 3d orbitals in the third energy level. So 1 plus 3 plus 5 comes out to 9 orbitals in the third energy level, and that is a maximum of 18 electrons that can be held in the third energy level. The fourth energy level, there's 4s, 4p, 4d, and 4f. There's only one 4s orbital. There are 3 4p orbitals. There are 5 4d orbitals, and there are 7 4f orbitals. All these numbers will add up to 16. Orbitals are found in the fourth energy level, and that is a maximum of 32 electrons that can be found in the fourth energy level. Now, if we try to make this look kind of Bohr model-ish, it might look something like this. Now, notice that each of these, I guess, parts of an orbit around the nucleus represents individual sublevels. So you'll notice down here we've got the 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. Each line does not represent an actual energy level. They're representing all the little sublevels. So if we wanted this to look more like a Bohr model that just had one orbit to represent an entire energy level, the second energy level might look something like that, the third energy level might look something like this, and the fourth energy level. But it's going to start looking less realistic for several reasons. One of them, most importantly, is that it turns out that several of these orbitals actually overlap each other, and also they're not circular in shape. They do not orbit around the nucleus. Electrons are not confined to a fixed circular path. Instead, they belong to these three-dimensional regions of space called atomic orbitals, with different kinds of shapes that can be calculated mathematically. So let's go ahead and look at these shapes. Okay, so goodness, it already looks like a mess. When we look at these different kinds of orbitals, some of them have recognizable shapes. For any energy level, that means rough distance away from the nucleus, where we expect to find electrons. Every energy level has an s orbital, and that s orbital is spherical in shape. So let's say we were saying the 1s orbital, and we'll just use a blue to represent it. The 1s orbital would be spherical in shape around the nucleus. So this circular or spherical shape that you see here, all this represents is the region of space where we'd most likely find an electron. So the first 2 electrons in any atom would be found closest to the nucleus in a spherical volume. Now that's where the first 2 electrons go, but what about the next 2 when we know that they go into the 2s orbital? Again, we're talking about the second energy level, which means we're looking at a distance roughly farther away from the nucleus. We expect to see more electrons. These are going to be also in a spherical shape, but it encompasses the entire volume, including the 1s orbital. So let's just sort of draw out here. So we know that all of this volume, including the volume in three-dimensional space of the 1s orbital, all this belongs to the 2s orbital. And I'll just kind of leave that inside there, just so you can kind of see how that first energy level, the 1s orbital is present, and you get the 2s orbital, which is a lot bigger. And then after we filled the 2s orbital, we'd then fill in the 2p orbitals. But let's just say, okay, what if we were going to move on to the next energy level? Where would we find the 3s orbital? Well, the 3s orbital, since we have that 3 in front, it means we're an even farther distance away from the nucleus, and it's also spherical in shape, and it encompasses the first energy level 1s orbital, the second energy level 2s orbital, and now we're talking about a much larger atom because there are electrons that are way out here. So it occupies all of this three-dimensional space, including the space that's being occupied by the 2s orbital, including the space that's being occupied by the 1s orbital. And every time we have a new energy level, the first orbital in that energy level to be filled is an s orbital, and we're looking at even larger and larger spherical volumes that encompass all of the other orbitals that are much smaller than it. Alright, now let's talk about the p orbitals. And for the p orbitals, let's focus over here in this space. Any energy level that has p orbitals in it has 3 different p orbitals. And they're just differentiated by their position in space. And we're just going to conveniently assign them by the axis that they're on. So again, for any energy level that has p orbitals, whether it's the second energy level, third energy level, fourth energy level, we're talking about 2p's, 3p's, 4p's. They have 3 p orbitals, and you've got one that is along the x-axis, z-axis, you've got one that's along the x-axis, and you have one that is along the y-axis. So what you might notice that for these, they look like three-dimensional infinity signs or dumbbell shaped. You might notice that for these, the closer they get to the center where the nucleus would be, the smaller or the less likely you're able to find the electron. It seems to have a much larger lobe farther away from the nucleus than toward the center. And we'll explain the reason for that in a little bit. But this is generally, if we connect this to the apartment analogy, here is your apartment building that has 3 apartments, and it's got enough space for 2 people in each apartment, and one person would fill in one at a time. Well, for electrons, you'd have an electron fill in one of the orbitals that is along a certain axis, then you'll have another electron fill in another orbital, and then you'll have the next electron fill in the last vacant orbital. Before, and then once they're all half filled, the next electron is going to have no choice but to fill in one of the orbitals that already has an electron, and so on until they're all filled with 2 electrons each. So you can see the 3 different individual p orbitals that can be found in any energy level. And then, of course, here we just have a composite of all 3 mixed together. Let me go ahead and erase all this. And now I'm going to make a composite of an atom that has s orbitals and p orbitals overlapping each other. Alright, so let's say we were working with a system that had 7 electrons, 7 electrons in a system. So we know that the first 2 would fill in the 1s, the next 2 would fill in the 2s, and then we'd have 3 remaining, and they're going to go ahead and fill in the 2p orbitals. So what would that look like in the atom? It would look something like this. We know that the first 2 electrons are found in the 1s orbital. So around the nucleus, spherical in shape, right? We would expect to see 2 electrons. So somewhere moving around in this 3-dimensional spherical space are 2 electrons. And we know that farther away from the nucleus, there are 2 electrons in the 2s orbital. Well, the 2s orbital is also spherical in shape and much farther away from the nucleus, so we're looking at an even larger spherical distance. And notice how we can't really see the electrons in the first one because they're so much closer to the nucleus. And moving around in this volume of space, we expect to see 2 electrons at given points, just moving around so fast that if we took a picture, we would see a blur that looks like this spherical shape. I mean, not an actual picture. I mean, we don't have the technology to take a picture of an electron. We do have some technology that lets us pick up on the, magnetic fields, but yeah, no. Now let's jump to the next set of orbitals, which is the 2p orbitals. Alright, so for the 2p orbitals, we know that we have 3 electrons in the 2p orbitals. Now, the second energy level consists of 2s and 2p orbitals. We know that the 2p orbitals are going to be a little bit farther from the nucleus, but not too far from than the 2s orbitals, because they're both in the same region of space, which is the second energy level. So I'm going to go ahead and pick the x-axis one first, right? So we know that as we get closer to the nucleus, there's less likeliness of seeing the electron, and as we get farther away, we're more likely to see it. So here we know that we have a p orbital along the x-axis. Mind you, we don't just draw it over the sphere because I want to kind of show you how they're overlapping each other. So we have this 2s and 2p orbitals that are within the same region of space, but the 2p and the 2s are sharing some of that space. But it makes sense that we're going to see 2p electrons more likely this far out from the nucleus than here, because if it was here, you have a lot of electrons already moving around within this space, that there's a lot of electron repulsion, and it's just going to be more likely found way out here in these bigger parts of the lobe. But we also have two other orbitals present. So a composite of the three overlapping 2p orbitals with the 2s orbital might look something like this. And we know that we have electrons in these 2p orbitals, and since it's 2p3 and we know that we fill them one at a time, we know that we can expect to find an electron in each of these orbitals. And then, of course, if we were to keep going, if we were to keep adding electrons to this system, then we know that we would have another electron in an orbital that has just one electron, and then the same for the other two orbitals. And now we have a situation where all of the 2p orbitals are completely filled. We're not looking at 2p6 anymore, 2p3 anymore. We're looking at 2p6. If we were to introduce the next orbital available, it would be the 3s orbital, which is an even larger sphere. So we're talking about, encompassing all of these electrons here, and this atom is just going to keep getting bigger and bigger and bigger, and I'm not even going to finish coloring all that. So you get the idea, or you should. All right. So far we know that as these atoms have more and more electrons in them, they occupy orbitals that continue to overlap each other. Before we get to a d orbital, we have to fill everything up to the 4s orbital. So by the time we get to the d orbitals, we're looking at atoms that are considerably much larger. Now, I'm not going to break down and do all the examples of the d orbitals because this is already going to be a pretty long video. But just some notes for you to keep in mind. For the s orbital, they're spherical in shape. We know for the p orbital, they are dumbbell in shape. And for the d orbitals, 4 out of the 5 are cloverleaf shaped, and the fifth one looks like a double-sided pacifier, which I think I drew over here. Yeah, so that's the fifth d orbital. Now, when we look at the f orbitals, they're even more complex. I'm not even going to draw them. But another note for you to remember is that for the s orbitals, there's only one type in every energy level. For any energy level that has p orbitals, there are 3 different p orbitals. For any energy level that has d orbitals, there are 5 different d orbitals. And for any energy level that has f orbitals, there are 7 f orbitals in an energy level. Goodness, this video is never going to end. Alright, so now let's get into electron configurations. The rules that you knew for the apartment complex, they have names for them. So let's go ahead and clarify them. First one is called the Aufbau principle. The Aufbau principle says that electrons fill the lowest available energy levels before filling other energy levels. Then we have the Pauli exclusion principle that says no more than 2 electrons per orbital. Then we have Hund's rule, which says every orbital in a subshell is singly occupied with 1 electron before any other one orbital is doubly occupied, and all electrons in singly occupied orbitals have the same spin. So hopefully you can get those analogies. You can connect that to the apartment analogy, right? So I think the first two are much more obvious, but for the third one person at a time, and each first person into the apartment had the top bunk. So that's the equivalent to having all of them, having an up or a spin up instead of one up, one down. And we'll see a couple examples, so we'll make sense of it. Don't worry. All right, so let's go back to this, and it got a little bit messed up from earlier, but this right here is called the off-bow diagram, and it basically it's a way to interpret the orbitals as they're being filled away from the nucleus. All right, so in these examples, we're going to be looking at where electrons can be found in neutral atoms. The idea is that in a typical atom, the electrons and the nucleus, they're going to interact in some way to make the most stable arrangement possible, least amount of energy as possible. Let's say we were going to do a neutral atom of phosphorus. Well, you would have to look at the periodic table and you'd have to say, okay, how many electrons are we working with for phosphorus? And since this is a neutral atom, your number of electrons and protons are the same. So the atomic number is the number of electrons in this example. So phosphorus has 15 electrons in the atom because it has 15 protons and it's neutral. So where do the electrons go in the off-bow diagram? Well, let's go ahead and put them in. We know that the first two go in the 1s orbital, one up, one down. The next two go in the 2s orbital, one up, one down. The next ones are going to go in the 2p orbital, and according to Hund's rule, they go one apartment at a time, and they have the same spin, so we're going to go ahead and point them in the same direction. Up, 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 and then we go back and double up, and they will have the opposite spin. So far we've spent 10 electrons. We have 5 more to go. Well, we know that we're going to fill the 3s, and then we have 3 electrons left, and they will go up, up, and up. So if we wanted to show the orbital filling in a straight line, it would look like this. And I apologize for not filling in the 2p in the order that it should have been. So the electron configuration for phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, where these subscripts are the number of electrons that are found in that energy sublevel. So in the 2p orbitals there are 6 electrons. In the 2s orbital there's 2 electrons. In the 1s orbital there's 1 electron. There's 2 electrons. And if we add up all those numbers, we get 15. Alright, let's get crazy. Let's do another one. Alright, if we did chromium, we would have 24 electrons to play with. And remember, that was one of your exceptions. So let's do chromium, but forget about it being an exception. Let's just go through the process. Well, if we did, we left off on phosphorus with 15. So if we just keep going, 16, 17, 18, 19, 20, 21, 22, 23, 24. If you said, okay, this is how I'm doing electron configuration, that's my configuration for chromium, this would be fine because you're telling me that you understand the process of how we do the atoms. However, it is an exception. It turns out that chromium naturally does not exist like this. Chromium would much rather have 1 electron in the 4s orbital and 1 electron in each of the 3d orbitals. This arrangement is much more stable because now you have 6 orbitals that are kind of close to each other, all same amount of energy, instead of 1 orbital with 2 electrons, 4 orbitals with 1, and then one with no electrons. There's a little bit more instability there. If we were to draw out the straight line orbital filling diagram, it would look something like this. And remember, for the 3D orbitals, they all have the same spin as they occupy those orbitals. So the electron configuration for chromium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Alright, so you're going to have to get kind of comfortable filling out these off-bow diagrams or doing the straight line orbital filling, and especially writing the electron configuration for any neutral atom. And luckily, there's a shortcut. Enter the periodic table. So just for the sake of making this easy, this is supposed to be helium, so I'm just going to go ahead and scratch it off, and I'm going to go ahead and insert it over here. Alright, not my best work, but that's okay. So we can look at the periodic table, and it just so happens to be conveniently organized in this fashion. The elements that are found in these first two columns make up what's called the S block. The elements that make up the last 6 columns, sorry, this periodic table is not up to date, makes up the P block. The elements that make up the inner transition metals are the D block, and the elements that make up the elements that make up the transition metals are the D block, and the ones that make up the inner transition metals are the F block. And we're already told where they fall: 1s, 2s, 3s, 4s, 2p, 3p, 4p, 5p, 4f, 5f, 3d, 4d, 5d, 6d. The last ones would be over here, your 7p. Okay, so how do we use this shortcut? It just so happens that the number of elements in a row in one of these blocks is also the maximum number of electrons that set of orbitals can hold. So for example, in any of the rows for the S block, there are 2 elements, 1, 2, 1, 2, 1, 2. For the P block, 1, 2, 3, 4, 5, 6. For the D block, 1, 2, all the way to 10. For the F block, 1, 2, all the way to 14. So we're going to take advantage of that. Instead, we'll just go ahead and look at a periodic table like this. What this shows us is the last orbital that has electrons for every one of these elements. For example, hydrogen will end in 1s1. Helium will end in 1s2. Lithium will end in 2s1. Beryllium will end in 2s2. Boron will end in 2p1. Copernicium will end in 6d10. Mercury will end in 5d10. Iodine will end in 5p5. So really, all you have to know is where it's going to end, and know that everything before it is going to be filled. So you just have to know the order in which orbitals are filled. And they are filled as you pass through that set of orbitals as you increase the atomic number. So for example, let's say we were going to do chlorine, which is 3p5. All the orbitals that you pass to get there have to be filled. We passed the 1s orbital. It's going to be filled, 1s2. We passed the 2s orbital, 2s2. 2p orbital, 2p6. 3s orbital, 3s2. 3p orbital, it's not completely filled. It stops at 3p5. So the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. The only ones you have to watch out for are the exceptions. So for example, chromium ends in 3d5, however the s orbital is not 4s2, it is 4s1. Same thing for copper. Copper, it ends in 3d10, however the 4s orbital is 4s1. So you have to be careful with those exceptions. and those are the only ones that you're responsible for. But if you look below, it turns out that there's some other funky business that happens with those, but you don't have to worry about them. Alright, goodness, that was a very long video. So, extra points to the first 3 people who, no, let's make it 5. 5 people who make it all the way to the end, but let's try to play the honor system here, right? So if you made it, you endured this entire video. Only the people who have fully endured all 40-some minutes of this video should earn those extra points. Don't tell your friends. Just send me an email, say, sir, extra points at the end of that video, and be honest and just let those first 5 people earn those extra points, and we'll go from there. All right, so get started on your homework.